Arc length can be approximated by connecting a finite number of points on the curve using line segments. The more points you use, the closer your approximation is to the true length. Here it is approximating with 1 point, and then with 2 points, and finally with 3 points. To approximate the length of the curve S, you add up the lengths of the hypotenuses of right triangles with sides delta x and delta y. If you want to find the exact length S of a curve y equal f of x on the part of the graph between x equal a and x equal b, consider the infinitesimal part of the curve ds. The Pythagorean theorem gives the length of the hypotenuse ds squared equals dx squared plus dy squared, or just ds equals the square root of dx squared plus dy squared. So then the formula for arc length is just the integral from a to b of ds. Taking the square root and then pulling out a dx squared, you get ds equals the square root of 1 plus dy squared over dx squared dx. So if you want to find the arc length of y equal f of x from a to b, you take the integral from a to b of the square root of 1 plus dy dx squared dx. Alternatively, if you define x in terms of y like x equals g of y, the formula for arc length from c to d becomes the integral from c to d of the square root of 1 plus dx dy squared dy. We can use this formula to prove that the circumference of a circle is 2 pi r. The equation of a circle is x squared plus y squared equals r squared, or alternatively f of x equals the square root of r squared minus x squared. The derivative f prime of x is 1/2 times 1 over the square root of r squared minus x squared times negative 2x by the chain rule, which equals negative x over the square root of r squared minus x squared. And then squaring this, we get x squared over r squared minus x squared. So we're going to integrate 1/4 of the circle from x equals 0 to x equal to r, and then multiply the final answer by 4. So, using our formula, we have the integral from 0 to r of the square root of 1 plus x squared over r squared minus x squared dx, which, after simplifying and pulling out the square root of r squared, which is a constant, becomes just r times the integral of 1 over root r squared minus x squared dx. Multiplying top and bottom by 1 over r lets you simplify really nicely because you get 1 over r over the square root of 1 minus x over r quantity squared in the integral, which is awesome because that's my derivative of arc sine of x over r. And then if you evaluate this from 0 to r, you get r times the arc sine of 1 minus r times the arc sine of 0, which is just r times pi over 2. Then, multiplying this by 4, you get 2 pi r, which is the formula for the circumference of a circle. So, for surface area, if we go back to the idea of approximating arc length with many line segments, we can rotate each of these line segments around the x-axis to get a solid whose surface area approximates the true surface area of the function on that interval. Each of the resulting segments is called a frustum, whose surface area can be found with the formula 2 pi rl, where r is the average of the bases and l is the slant height of the frustum. In our function, the surface area of one frustum becomes 2 pi times y1 plus y2 over 2 times the square root of delta x squared plus delta y squared, which in the limiting case is just 2 pi times ds times y. So, to find the surface area of a function revolved around the x-axis on the interval a to b is 2 pi times the integral from a to b of y ds. Similarly, if you'd revolve the function around the y-axis, you get 2 pi times the integral from c to d of x ds. In both of these formulas, you can use either of the two previous definitions of ds, depending on which is easier to solve for with the function you're given. We can use these to find the surface area obtained by revolving the curve f of x equals the square root of x around the x-axis from 1 to 4. Taking the derivative, we get 1 over 2 root x, and squaring, we get 1 over 4x. Using the formula for surface area, we have 2 pi times the integral from 1 to 4 of root x times root 1 plus 1 over 4x dx. Simplifying this and pushing the 2 into the integral and into the square root, we get pi times integral from 1 to 4 of root 4x plus 1. Using the wishing game, we see that under the radical is 4x plus 1, whose derivative is 4, so we wish for a 4 and put a 1/4 on the outside. And then integrating, we get pi fourths times 2/3 times 4x plus 1 quantity to the 3/2, and evaluating from 1 to 4 results in pi 6 times the quantity 4 times 4 plus 1 to the 3/2 minus 4 plus 1 to the 3/2, or just pi 6 times 17 to the power of 3/2 minus 5 to the power of 3/2. Arc length is the integral of ds. If you have y as a formula of x's, ds is the square root of 1 plus dy over dx squared dx, and if you have x as a formula of y's, ds is the square root of 1 plus dx over dy squared dy. Surface area is 2 pi times the integral of y ds for rotation about the x-axis and 2 pi times the integral of x ds for rotation about the y-axis, where you can use either definition of ds in either formula.